carries on with our ideas about waves, but this time it's focusing mostly upon sound and sound waves. Now, I think on a previous video I talked to you about what sound waves were, what type of waves they were, and we represented them as if you were looking on top of a slinky and you were looking down on the slinky. And we essentially said that the particles are actually moving back and forth. This is their vibration, and that transmits a wave in this direction. And so therefore, when you have that combination happening, we call these longitudinal waves. Now, longitudinal waves are, if you were asked for an example of a longitudinal wave, then you always say sound waves, because that's just the perfect example of a longitudinal wave. That seems pretty regular, there's no waves happening, so let's imagine we had a wave happening like that. And here we go, and finally another one happening there. Remember we said these are the compressions. And these are very advanced terms, which you won't need, but rarefactions. Okay, now, obviously what sound needs is sound vibrates. The vibration of sound, but what is it vibrating? Well, when you're listening to my voice now, that's vibrating the air. So you can have air being vibrated. Similarly, you can also have liquid being vibrated, and, believe it or not, solid being vibrated. And they give rise to very different properties because, for one, they have different, I suppose, properties in that air is very spread out, with particles moving around randomly. Liquids are contained within a vessel in which particles move around, but they're more closely packed. And in a solid, the particles are fixed closely together and they vibrate around their rest points. If a vibration is one particle giving information to the next one and bouncing that information along, then it happens so much more quickly in solids because solids are more dense. Solids are denser. Whereas air is less dense. And liquids are somewhere in between. But the point is about its density. How densely packed is it? So therefore, sound travels quite poorly in air in actual fact. The speed of sound is 340 meters per second. And you ought to really memorize that because that's a really important speed to bear in mind. I'll just circle that. Liquids, it must go faster because it's going to be more readily bumping into them. So it's actually going approximately, let's say, 1,500 meters per second. And in solids, though it varies, it's approximately 3,000 meters per second, just off the top of my head. Very fast, more dense. You can see we have an increase in speed as we move towards the denser materials. That's also a good example why you hear trains arriving at stations before you see them, because the sound travels along the tracks much more quickly than the air. So you won't hear the train arriving, you'll hear the tracks, the sound through the tracks, because it travels about 10 times faster in the tracks than it does through the air. And also this gives rise to what happens in a vacuum. Well, what's being vibrated in a vacuum? Well, first of all, what's in a vacuum? A vacuum has no particles. And if there's no particles, you can have no sound. We had that example of we had a bell jar, and you evacuated everything in the bell jar, and you had it's a bell jar because it looks like a bell, and also there was a bell suspended in it, and a hammer hitting the bell, and the noise would travel out, but without anything inside, you didn't get any sound on the outside as the air was being sucked out. So in a vacuum, no particles. So therefore, if you're in space, for instance, even if two astronauts are standing very, very close to each other and shouting, they won't hear each other. They have to have radios between them, because radio waves can travel in a vacuum, and we'll come on to that in the next video. Okay, now whilst we've got this moment, we'll talk about the speed of sound here in an experiment. So let's work it. So an experiment to measure the speed of sound. Okay, you've done this in class, but I think it's worth mentioning. Again, you can find a wall, and this technique is not just used for measuring speed of sound, but also with echolocation or underwater sonar, so on and so forth. And you can make a noise, and that noise will travel out, strike the wall, echo, i.e. reflect, and come back, and you can hear the echo. Now, if you know the distance you are from the wall, let's say, for instance, it is 330 meters. How convenient is that? And the time it took, because you make the noise, hit timer go, and it comes back to you, is, let's say, 4 seconds. No, we want it to be more. We want it to be about 2 seconds. Then what would the speed of sound be? Well, if you think you know, hit pause. Whereas if you don't, or you're checking your answers, here comes the answer. The speed of sound is going to be the distance divided by the time. Now the distance that's been travelled is 330 meters, but careful here, not only has it gone that way, it's bounced and it's travelled back again. So in actual fact, it has travelled twice the distance. And the time is 2 seconds. And if you plug that into your calculators, you come out with 330 meters per second. Interestingly as well, we showed this in the lesson. If you had the Earth and you had the Moon right off here, and in the YouTube clip of the Big Bang Theory, they said that they sent out a laser pulse and it bounced off one of the reflectors on the Moon, because man had left reflectors on the Moon, and it came back. Now the speed of light, which is given the letter c, is 3 times 10 to the 8 meters per second. And they said in the Big Bang Theory that time was 2 seconds it took. So what's the distance? If you think you know, hit pause. Otherwise, here comes the answer. Well, it's going to be the velocity times the time, which gives us 3 times 10 to the 8 times 2, which is 6 times 10 to the 8 meters. 600,000 kilometers. But if you Googled it, you'd realize that it's not. It's only 300,000 kilometers. Why is that? Well, you've measured the distance from the Moon and back again. So really, you're looking for half the time it's taken, because that's how long it's taken to get there. If we divide that by 2, that gives us 3, which is the right distance. Okay, let's move on a little bit. We're going to look at how we can actually represent sound in a signal. Let's imagine I have a microphone. That looks more like a tree. Sorry, so there's my microphone. And it receives some sound. My microphone can be connected to an electrical device that reads it, which we call an oscilloscope. And what the oscilloscope does is that it changes my longitudinal wave which is the vibration of sound, and it changes it into an electrical signal. And that electrical signal is displayed on the oscilloscope. Now what an oscilloscope is, it's just a screen with lots of squares on it. I'll explain those squares in a minute. It has lots of squares, not just in columns, but in rows as well. and it produces a little dot on the screen, and the dot will go up and down, and what happens is it's producing what's known as a trace on the screen, and that trace is a product of the time axes, measured in seconds, and this is the voltage. You won't actually see any axes on the screen, you just see a trace, but it's showing the voltage, so an electrical signal. So the greater the amplitude of the wave, the bigger the voltage against the time. Now please look here. We have a longitudinal wave and what looks like a transverse. Okay, but sound is a longitudinal wave, not a transverse wave. This is just the oscilloscope's way of showing the type of wave that it sees. But in this position you can do a lot, because if you think, if you can recognize this, that looks very much like what we did in oscillations. Okay, so in the oscillations topic, you could work out from here the period of the wave, which is the time for one wavelength, one wave to occur, and you could work out the frequency, number of waves per second. Sorry if that's small writing, but obviously that is just a quick recap. Do you also remember how you related the two? T is 1 over F. That was the equation used. So you can work out the frequency of sound. Okay, let's show you another example of how that works. So, an oscilloscope. Let me explain it a little bit more. Okay, you will be shown a trace on a screen. And the reason why we have all these dots, which are these squares, is because you can set the meter, the oscilloscope, to control the sensitivity of these. And you have little dials to do that. Those little dials point at something, and you probably have around here something that says something like 10 seconds, 1 second, 0.1 of a second, 1 millisecond, 1 microsecond. And as you change the position, so you change what this square represents. So this is for the x-axis, which is time. You can do the same for the voltage as well, but it's less interesting. I should probably say less interesting for this topic. We might use it later on in the course. Okay, just what does micro mean? Okay, let me just write those down as another aside, which is important for us to consider. These ideas of scientific terms. If we had we can have 1,000 times greater than something, which we conveniently call kilo, and is also given the standard form of 10 to the 3. You can have a mega as well, which is 1,000,000. And because obviously writing all these things is much harder, we use standard form, which makes life easier. The 6 implying 1, 2, 3, 4, 5, 6 decimal places. It's jumped 3, 1, 2, 3. Mega kilo is if scientists want to talk to each other. They go, oh, it was so many megajoules, it was so many kilojoules, it was so many. But we do the same above 1 and also below 1. And we give these symbols. Mega is capital M, kilo is capital K. And then we can go milli, which is smaller m, which is actually 1,000th. gives the 1 times 10 to the minus 3. And then we can go micro, which is given 1 over a million, which is 1 times 10 to the minus 6. So you can see, and this keeps going up, and you can go to giga, tera, all the way to peta, zeta, and so on. And likewise, you can go to pico, you can go nano, pico, femto, etc. But those are the major ones that you'll come across. Okay. But with that in mind, let's draw a trace of a wave that might pop up on an oscilloscope. And let's see if we can describe that wave. Oh, I've done it very badly. Hopefully that's okay. Let's imagine that this arrow is now pointing to the millisecond. My question to you is, what is the time period of this wave? Bear in mind, remember we're on a time axis and a voltage axis. What's the time period of the wave? If you think you know, hit pause, otherwise here comes the answer. Well, I know the period of wave is between there and there, which is meant to be 2 squares. So I have 2 squares, and each square represents 1 millisecond, which is the same as 2 times milli 10 to the minus 3. Gives me 2 times 10 to the minus 3 seconds, or if you want, 2 milliseconds. Straightforward, but it's really useful. I could change this to get microseconds and work out those precise details as well. Okay, what's the frequency of the wave? If you think you know, hit pause, give it a go, otherwise here comes the answer. Well, we know that frequency is 1 over the time period. So therefore 1 divided by 2 times 10 to the minus 3, our answer before, gives us, I've got to do it in my head now, 500 Hertz. I hope that's right. Plug it into the calculator and see if it's right. Great, so really useful tool to use. Okay, now with sound, there is 2 more things that we need to think about. And one is, when we've talked about the amplitude in waves before, talked about the amplitude, when we're talking about sound, so that's a general term, and it still holds true with waves, but in terms of sound, the amplitude refers to the volume. When we talk about the frequency of a wave, we're talking about the pitch of the sound. So, let's imagine we wanted to draw a quieter wave with the same pitch on this plot. What would that look like? If you think you know, hit pause, otherwise here comes the answer. Quieter wave with the same pitch means it's got less amplitude, but it has the same frequency, or if you like, the same time period. Okay, let's get a louder sound with the same frequency. If you think you know, hit pause, otherwise here comes the answer. It gets louder, same frequency. I imagine you finally know what I'm going to ask you to plot, or attempt to plot. Okay, to make it a real mess, last but not least, let's make a sound with a higher frequency and a higher volume as well. Higher pitch, higher volume. You ready? If you think you know, hit pause, otherwise here comes the answer. Okay, there you go. So it's got a greater amplitude and it's got a smaller time period or a higher frequency. Okay, before I make that look like an utter mess, I think that's all you need to know for sound. Most of it hopefully we've covered in the lesson.